All right, hi guys, Mr. Austin here with another Algebra 2 lesson. Today we're going to take a look at lesson 4.6. 4.6 is called complex numbers. Now these are going to be numbers that we have not mentioned up to this point. So bring your A game today, pay close attention, and here we go. So if we have a system of numbers and we call them real numbers, we've been talking about these throughout the way. Real numbers, that means that there are imaginary numbers. Now, wait a minute. If there are real numbers, then there have to be imaginary numbers. Well, that sounds a little strange, but the answer to that question is surprisingly yes. Yes, there are. Hang with me. Let's talk about this. Real numbers. All numbers on the number line, that includes, but is not limited to, positives, negatives, integers, rationals, square roots, cube roots, pi, etc. Those are all real numbers. And real numbers are indicated by that big R. I've drawn it before. You've seen me draw it on the board before. Just to get an idea of what it looks like, it's actually, here's what you'll see when I draw it. That's the real number symbol. And you can see that that's what's on your notes there too. Real numbers are easy to understand because we see them a lot and we use them a lot. They are included in most of the math problems that we have solved so far. Wrong. So-called imaginary numbers are as normal as every other number, or just as fake. I know that sounds confusing. So they're a tool to describe the world in the same spirit of assuming like -1, 0.3, and 0 exist. Because let's think about this, as people were developing this idea of numbers, you know, I can imagine someone sitting there saying 1, 2, 3, 4, 5, and then all of a sudden, out of nowhere, someone says, hey, how about -1? And people probably thought that was really strange. Or how about 0.3 or 0? And again, not knowing any of that, that might be strange in the beginning. So let's just assume that some numbers called I exists. I obviously stands for imaginary. And here's what I want you to know. If I exists, and we're just going to go with it, we know that it does. I exists, it's the imaginary unit. Here's what that means. I squared will equal -1. Something important to know. I squared will equal -1. So here's what we want you to know about I. I is the same thing as the square root of -1. We'll see that here in just a minute. So I squared then would be -1 because when we square a square root, it basically just cancels it out and takes it away. So that would mean that I squared would equal -1 if we did that. So that is, if you multiply by itself to get -1, what happens now? So let's take a look. Well, first we get a headache, of course, because we're thinking of this. Wait a minute, Austin, this is imaginary numbers, and this is all crazy, but just hang with me just a moment. Let's pretend that I exists. New relationships then can emerge if we decide that, yeah, okay, I'll go with this I idea. You may not believe in I, just like those old mathematicians didn't believe in -1. New brain-twisting concepts are hard, and they don't make sense immediately, even for some genius mathematicians. But as negatives showed us, strange concepts can be useful. So let's take a look at what this is all about. Mathematicians created an expanded number system, and they called it the imaginary numbers. They based it upon the idea that the letter I would represent what we call the imaginary number. Take a look. I told you earlier, I is going to equal the square root of -1. We call that the imaginary unit. Using that information, I want to go through a few things with you so that you know what they equal. Like, for example, I squared. So we just said earlier, if you take I and you square it, and you know that I is the square root of -1, that means you're taking the square root of -1 times the square root of -1. And that simply equals -1. Now, if you can't follow that, let me just give you an easier one. The square root of 2 times the square root of 2 is the square root of 4, which is actually 2. The square root of 3 times the square root of 3 is actually the square root of 9, which is actually 3. Following that same pattern, the square root of -1 times the square root of -1 then would equal -1. And that's what we're going to go with. So then we bring about this idea of the square root of -1 cubed. So I'll write it out, square root of -1 times the square root of -1 times the square root of -1. Well, we just learned earlier that the square root of -1 times the square root of -1 gives us -1. So that means that these two give us -1. If that's the case, then wouldn't we have -1 times the square root of negative 1. Yeah, we would. And we know up here what the square root of negative 1 equals. It actually equals I. So really, don't we have just negative 1I? Yes, we do. So the answer to the I cubed is negative 1I. Now, follow my logic here. Negative 1, or negative I to the fourth is the square root of negative 1 times the square root of negative 1 times the square root of negative 1 times the square root of negative 1. Remember, we just learned earlier that the square root of negative 1 times the square root of negative 1 is negative 1. So that would mean really what we have is negative 1 here and a negative 1 here. And a negative 1 times a negative 1 actually equals a positive 1. Interesting. Okay, so next, let's do I to the fifth. Well, now we can start thinking about this a little differently. I already know I to the fourth. I to the fourth is 1, so that's 4 of them. That's 4 of them. 4 of them equals 1 when you multiply them together. But we got 5, so that means we got 1 more, square root of negative 1. And remember the square root of negative 1 we said was I, so 1 times I is simply 1I. So this equals 1I. Okay, so now we know what I to the fifth equals. Well, now we want to know I to the sixth. Well, think of it this way. If we do I to the sixth, I think it's easier if we write them all out so we can show them to you. That's going to be the square root of negative 1 times 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 the square root of negative 1 and one more times the square root of negative 1. Now keep in mind, each pair of these, we already said, is equal to negative 1. So if each pair is negative 1, that's negative 1 times negative 1 times negative 1, which is simply negative 1. Interesting, we had negative 1 up there for I squared. I wonder if this pattern is starting to repeat. Well, let's check and see. Remember, we already know I to the sixth, so we're going to multiply one more and get I to the seventh. So that means that we're going to have negative 1, because that's I to the sixth, times one more of these, square root of negative 1. And remember, the square root of negative 1 is I, so this is actually negative 1I. It sure looks like our pattern's starting to repeat. If you look above, well, let's check one more. We got 8 of them, so that's 4 pairs. And again, I'll write it out, but it'll be a little ridiculous. The square root of negative 1 times 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 the square root of negative 1. That's 1, 2, 3, 4, 5, 6, 7. And one more is the square root of negative 1. Remember that each pair, 2, 3, 4, each pair equals negative 1 when you multiply them together. So negative 1 times negative 1 times negative 1 times negative 1 is simply 1. So yeah, you can see it's starting to repeat over and over again. So now that we've figured out how to multiply these i's together and the square root of negative 1, let's see why we need these. Well, early on we used a tree method to break down these square roots. We're going to do the same thing this time. So what I'm going to do is I'm going to draw up my tree method. And I look at this and I say, well, negative 3, well, 3 doesn't break down. But there's a negative underneath there. So I got to get that negative out from underneath the square root, because we know you can't take the square root of a negative number. Well, how do we do that? Well, we can think of it this way. We know we could multiply the square root of negative 1 now times 3, and that would give us the square root of negative 3. But we also know that the square root of negative 1 is this new number we called I. And we also know that the square root of 3 won't break down anymore. So really what we have for our final answer here is I times the square root of 3. And by taking that I and putting it outside, I just believe, and you can see it easily, that basically pulling the I out from underneath here and bringing it out and putting an I out in front takes the negative away, which becomes positive 3 up there. Let's try it this time. The square root of negative 4. Well, again, I want to take that negative and bring it outside. It becomes I, because remember, it becomes the square root of negative 1, which is just I. And now I know the square root of 4, which is 2. So this answer is 2I. Okay, let's try with this one. First thing I want to do, I think the easiest thing to do is Pull your I out in front. And that leaves you the square root of 12. And now we can work with the square root of 12 by breaking it down using our square roots, which would be the square root of 4 times the square root of 3. And remember, we've still got this I out in front. All right, now this stays out in front. The square root of 4 is now 2, and the square root of 3 doesn't break down at all. So what we now have out in front is 2i times the square root of 3. And now we've simplified a square root with a negative in it, because we can pull that negative out and call it I. That's why I helps us simplify these numbers. All right, a complex number. Basically, a complex number is made up of two parts. It's made up of the imaginary part, and it's made up of the real part. So complex numbers are made up of both imaginary and real parts, as you can see in the example above. All right, using this concept, let's take a look at these. Adding what we call complex numbers together is actually really simple. We use this idea and we call it like terms. This term and this term, they're like. They both have an I in them. We can treat that I like it's a variable. And then, obviously, the other two, 10 and 12, are like terms. So if I'm going to write my answer to this, I can simply add the like terms together, which makes this a really easy problem. 10 plus 12 is 22. And negative 7i plus 9i is 2i. There's the answer. And it is, again, a complex number. So I added two complex numbers together, and I got a complex number. How about multiplying? Well, we're going to use our generic rectangle for this. We're going to multiply these two quantities together. I wonder what would happen if you multiplied a complex number times another complex number. Well, we're about to find out. All right, 2 times 4 is 8. 2 times 2i is 4i. 4 times negative I is negative 4i. And here's where a lot of people make their mistakes. This is going to be 2 times negative 1, which is negative 2. I'm not going to write it yet. Actually, I will write it, and then I can just erase it for you. It's negative 2. But remember that I times I is I squared, and we learned earlier that I squared is negative 1. And when I multiply that by negative 2, I actually get positive 2. So this answer is actually positive 2. Again, let's try it again. It's 2 times negative 1, which is negative 2. And then I times I is I squared, which is negative 1. And negative 2 times negative 1 is positive 2. Cannot forget that sign change. All right, we got some like terms right here. A positive 4i and a negative 4i. Well, they're just going to cancel each other out. So therefore, they're gone. And all we've got left is 8 plus 2. Interesting. We multiplied two complex numbers together and we got a real number answer. That's pretty fascinating to think about. That you can take an imaginary number and a whole number and put them together and call them a complex number. And then when you multiply a complex number times a complex number, you actually get a real number answer. That's pretty interesting. All right, let's take a look at this. How are we going to solve this? Well, we've learned earlier that why don't we just take the square root of both sides? So that gives me t minus 2 set equal to, since we're taking the square root of both sides and solving for t, we know it's going to be square root of negative 16 is going to be plus or minus something. We'll call it plus or minus the square root of negative 16 right now. It's because this is your notes. Now we learned that, hey, we've got to break this square root down. Well, first thing I want to do is get rid of that negative sign. To get rid of that negative sign, we've now learned, just take an I out front. And now we know the square root of 16 is 4, so t minus 2 equals plus or minus 4i. And the last step is to add 2 to both sides. So here we go. T is going to equal 2 plus or minus 4i. Remember, if we want to see both of those answers, it's 2 plus 4i and 2 minus 4i. That's what the plus or minus does for us. It gives us our two answers. Okay, let's subtract a couple of these. Remember that when we subtract, it's almost like this is negative 1 being distributed on there. So really what we got is 6 minus 8i minus 4 plus 6i, because a negative and negative becomes a positive. Now if I look, I've got a 6i and a negative 8i. I've got a negative 4 and a positive 6. So let's put our like terms together. 6 minus 4 gives me 2. Negative 8i plus 6i. Oh, sign wrong. Negative 8i plus 6i actually gives me negative 2i. Complex number answer when we subtracted them. Now when we divide, division gets a little interesting. We know that in division, here's the rule. You cannot have an I in the denominator. You might want to make a note of that. No I in the denominator. Can't have it. There is no i's in the denominator. So in order to get rid of this I, here's our idea. What about if we multiply that I on the bottom by I, and that means we multiply the top by I, because I over I, anything over itself is 1, and multiplying by 1 doesn't change anything. So really, I over I is just 1. So we're multiplying this fraction by 1, but we're calling it I over I. That's going to give us 8i over I squared. Remember what I squared was? Yeah, that's right. It's negative 1. So 8i over negative 1, which is the same thing as negative 8i. There you go. And now we no longer have I in the denominator. That's called rationalizing the denominator. Last example of that. In the bottom here, when you've got these two connected by a minus sign, don't forget, that means they go together. So I like to put parentheses around them. And now I want to be able to, again, get that I out of the denominator. We're going to multiply the bottom of this by 3 plus I in order to get that I out of the denominator. So we're going to multiply it by 3 plus I. It's kind of like the opposite of it. And if we do that on the bottom, don't forget we have to do it on the top. All right, let's start with the numerator. Well, this is easy. This is just simply a distributive property problem. And that's going to give me negative 15 minus 5i in the numerator. Now, the denominator is a little more complex. I'm going to go to the generic rectangle for that one. We're going to have 3 minus I and 3 plus I. That gives me 9 minus 3i and then plus 3i. And then remember, a negative times a positive is a negative 1, but I squared times I squared is also negative 1. And negative 1 times negative 1 is positive 1. Let's put this together. Our like terms actually cancel out here. And all we're left with is 9 plus 1, which means we have 10. And that 10 is what we have in the denominator. So there it is. So our final answer does not have an I in the denominator. It's negative 15 minus 5i all over 10. And that is how you rationalize the denominator. All right, hopefully we're using some of these notes and some of the stuff we've talked about. You're now a little more comfortable with working with the imaginary unit.